AET 114, Chapter 18, Problem 4, Mesh Analysis, or Section 4. This is Problem 6. It says write the mesh equations for this network. Okay, there's a voltage source, an independent AC source, another independent AC source, and then you have a resistor, a capacitor here, and another capacitor here. So the first step, I drew my arrows with my loop currents, I1 and I2 here. And then I do KVL around loop number 1. So I like to start off at the lower left corner for consistency. So as we go through here, this is a voltage rise. We're going from minus to plus. So that's a positive E1. And then the next voltage is a drop across resistor R, which is going to be I1 times Z1, with Z1 defined to be 50 or 50 angle 0. And then continuing around this loop, going down through here, this is another drop across this capacitor. That's going to be, we're going to call that capacitor Z2, which is going to be minus J40 or 40 angle of negative 90. So that'll be minus Z2 times the quantity of I1 minus I2, because in the center branch, I1 is going down and I2 is going up. So they're going in opposite directions. And then finally, there's a drop across E2 because we're going from plus to minus. So that's minus E2 equals 0. So when you solve this algebraically and simplify it into the form, like this form, A times I1 plus B times I2 equals C, you get this equation that I have in blue. After doing some algebraic manipulations, here you're just combining, you're just distributing and then rearranging some terms. And then the last step, you multiply both sides by -1. This is the equation that you get for loop number 1. I call that equation 1. And likewise, you do KVL around loop 2. Again, I start at the lower left corner and work my way clockwise. So this is a voltage rise plus E2, and then a voltage drop minus Z2 times the quantity of I2 minus I1, because we're going in the direction of I2 and I1's going in the opposite direction. And then continuing on, we have another drop of minus Z3, which is this capacitor, which is minus J60 equal to 60 angle of negative 90. And then that times I2 equals 0. Remember, these are all voltages. Each one of them is a voltage. You have this voltage, and then you have this impedance times this current, and this impedance times this current. So you have to make each one of these a voltage. Doing anything else doesn't make any sense. This is an equation of voltages. So again, rearranging using algebra, I end up with this equation, which is in this form again, with a constant or a coefficient times I1 plus another coefficient times I2 equals another variable. So this is the second, we'll call that equation 2. So then using determinants, where we have basically two equations that look like this. This is equation 1, this first one, and then this is equation 2, where A equals Z1 plus Z2 from right there, B equals Z2, C equals E1 minus E2, D equals minus Z2, E equals Z2 plus Z3, and then F equals E2. So then you write your determinant to find your currents. So this is what the determinant would look like. You would have to put in all these values and do the multiplication, but you see how I did that. Then you cross multiply like so. C times E minus F times B in the numerator, and then the denominator denominator a times e minus d times b. And once you do all of that math, you end up with the answer. The answer that they gave for I1 is the current through the 50 ohm resistor. They called it I 50 ohm is 145.45 milliamps, angle of 187.59 degrees. So remember, all these numbers, all these numbers are complex numbers. You have to substitute these variables into this determinant and then do your multiplication and addition or subtraction. And for your z variables, then you have to put in these actual numbers in there to generate this answer. Okay, so this is a lot of math, a lot of chugging with the calculator. You definitely need, again, you need the calculator to do all this calculation. It's just too much to be able to do it by hand.